Welcome to this presentation on using modern graphical interface instruments to simplify component selection with robust DC characterization. My name is Ching Starks, and I am a product marketing manager at Tektronix. Let's begin our discussion. Today's design engineers are faced with numerous challenges to meet the many demanding application requirements. It is important that the designers select the right components and often test them beyond the datasheet specifications to determine to what extent the components can be used. The designer is also concerned how passive components have an impact on their circuit designs. Once the design is prototyped, the designer needs to know how the design works under various operating conditions. And during this process, there will be countless hours for debugging, continued prototype development, and learning what can go wrong with the design. The design engineers also faced not just with the engineering challenges, but the business challenges of getting the new product to market quickly and in shorter periods of time. And finally, he or she has to stay current on the latest design techniques and know how to use the latest measurement tools to shorten their design time. Many different semiconductor components are used in a single design. Components are routinely characterized to extract specific parameters so that the components the designer wants to use can be properly selected. For diodes, rectifiers, transistors, buck and boost DC to DC converters, some of the typical characterization and selection parameters can be seen here. The parameters that can be extracted range from as simple as the reverse breakdown voltage on a diode to the family of curves on a MOSFET to the DC current gain on a BJT. Let's discuss the characterization and the selection of these commonly used 2- and 3-terminal devices. The relationship of the current through a 2-terminal device and the voltage across its terminals is called the current voltage or IV characteristic of the device. Testing 2-terminal devices requires sourcing either a voltage or a current and measuring the resulting current or voltage. These source and measure operations are performed at multiple points and the data plotted with voltage on the x-axis and the current on the y-axis to create an IV curve. These curves provide the designer's insight into the performance of the device. For example, the graph on the right shows the characteristic IV curve of a diode. IV characterization is performed on diodes to determine key operating parameters like the forward operating voltage, reverse breakdown voltage, and the reverse leakage current of the diode. Selecting diodes is typically done by configuring instruments to perform sweeps. In a sweep, the source level is configured to automatically sweep from one source value to another in a discrete number of steps, and a measurement is made at each step. Performing sweeps with traditional instruments like power supplies and DMMs can be quite confusing for first-time users and even experienced users alike. To perform a sweep with these instruments, the power supply must be set up to output a series of voltages and the DMM configured to measure the resulting current. Triggering between the two instruments can be configured to synchronize the source and measure operations, and the timing of these triggers must be configured properly to ensure the source settles before the measurement is made. Due to the complexities involved with working with two separate instruments, many users often will write custom instrument control software to automate the tests and simplify data management. But this requires programming skills as well as learning the instrument's command set. Selecting 3-terminal devices has many similarities to the selection of 2-terminal devices. Current or voltage is swept at a pair of terminals and the resulting voltage or current is measured. However, with 3-terminal electronic components, the current voltage relationship at one pair of terminals is dependent on the current or voltage on a 3rd terminal. For example, on a metal oxide field effect transistor, or MOSFET, the IV relationship between the drain and the source terminals is dependent on the voltage present on the gate terminal. This relationship is usually displayed on a more complex current voltage graph with multiple curves, commonly known as a family of curves, each one representing the IV relationship of the terminal pair at a different current or voltage value on the third terminal. Characterizing MOSFETs and other three-terminal devices' current voltage parameter is crucial to ensuring they work properly in their intended applications and meet specifications. In addition to the family of curves for the transistor, the designer or the component engineer selecting components will also be concerned with the device leakage performance. With the proper instrumentation, if you measure the leakage current yourself, you would find that these devices often leak only in the nanoamp range and even as low as the picoamp range. If manufacturers wish to keep improving the leakage performance of their device, being able to measure current in these low ranges is required. Fortunately, modern instruments like the source measure unit have the capability to characterize typical leakage current even at kilovolt levels. We'll go into the details of a source measure unit, or SMU, shortly. Measuring gate leakage is one test that is very difficult to do on a traditional curve tracer, but is very easy to do with SMUs. Measuring gate leakage requires sourcing of voltage on the gate terminal with the drain and source terminals grounded, and then measuring the current into the gate. The curve tracer step supply does not support measurements, so the connections to the device must be changed so that the gate is connected to the curve tracer's collector or drain terminal for current measurement, and the MOSFET's drain and source terminals are connected to common. Still, this doesn't work very well because measuring gate current requires measuring low currents. Assessing the low current ranges on the curve tracer requires using the high voltage supply, but the smallest volts per division setting on the high voltage supply is 50 volts per division. Considering that most gate leakages are measured at 20 volts or less, this isn't very practical. Sourcing only 20 volts or less is easy with the high current supply, but the lowest current measure range is 500 milliamps per division. This is much too large to measure any kind of leakage current. Testing three-terminal devices like MOSFETs often involve the use of several instruments, including a sensitive ammeter, multiple voltage sources, and a voltmeter. Source measure units simplify three-terminal device testing by combining source and measure operations into a single instrument. But at least 2 SMUs are required to test a three-terminal device. Integrating, programming, and synchronizing multiple instruments can be tricky and time-consuming. When integrating together multiple instruments, the programmer has to consider parameters such as timing behavior of the instruments and the device and the setting proper ranges and offset corrections in order to get the proper results. Three-terminal device tests require writing programs or configuring pre-written test software to source voltage or current in a certain range, then measure the current or voltage relationship. With so many variables on how a test can be configured, most of the time required to test a three-terminal device is spent performing the setup. Energy efficiency standards worldwide have motivated engineers to find ways to design more efficient semiconductor devices, integrated circuits, and power systems, including power supplies. New energy-efficient semiconductors, such as a DC-to-DC converter, require testing to evaluate parameters such as output voltage, low current, off-state current, maximum power, and power efficiency versus current. Power is a calculated measurement and requires measuring the voltage across the device as well as the current through the device. You can then multiply the voltage measurement by the current measurement to calculate the power. Efficiency is the ratio of power drawn out of the device to the power sourced into the device. Calculating efficiency requires measuring power at both the input and the output of the device. The equipment required to measure power depends on if you are measuring a device's power consumption or if you are measuring a device's power output. To measure power consumption, you'll need a voltage source to source power into the device and an ammeter to measure the current drawn by the device. To measure the power output of a device, you will need a voltmeter to measure the voltage output, an ammeter to measure the current drawn by the load that is actually drawing power from the device. The need for all these pieces of equipment can make power measurement a real chore. Thanks to source measure units, measuring power is pretty straightforward. Measuring efficiency, however, is a little more involved. Efficiency measurements require power to be measured at both the input and the output of the device. Thus, multiple instruments are required. Since the power measurements at the input and output are performed by separate instruments, the efficiency calculation often must be done manually, as traditional instrumentation has no way to share the data with another instrument, and therefore cannot perform calculation for you. For calculating efficiency at a single low current, this is not a big deal because the calculation is simple. However, device characterization requires measuring efficiency at multiple low currents, and this manual calculation quickly becomes burdensome, not to mention a potential source of error. To alleviate these issues, a PC with custom test software is often used to automate the process, but this requires the user to have knowledge of the instrument's command set as well as PC programming skills to create the custom test software. During my discussion, I mentioned that a source measure unit can be used to characterize and help in the selection of board-level components. Let's explore what a source measure unit is. Stated in the simplest possible terms, a source measure unit instrument integrates the capabilities of a precision power supply with those of a high-performance digital multimeter. For example, SMU instruments can simultaneously source or sink voltage while measuring current, and source or sink current while measuring voltage. They can be used as standalone constant voltage or constant current sources, as standalone voltmeters, ammeters, and ohmmeters, and as precision electronic loads. Their high-performance architecture also allows using them as automated current voltage or IV characterization systems. The real benefit of SMU instruments for test and measurement applications come from their ability to source and measure signals simultaneously. When compared with using separate instruments to handle each function, SMU's simultaneous operation provides for faster test time, simplified connections, improved accuracy, less complex programming, and a lower cost of ownership. Their tight integration lets them protect the device under test from damage due to accidental overloads, thermal runaway, and other dangers. It also makes SMU instruments ideal for characterizing and testing semiconductors and other nonlinear devices and materials. Assembling separate power supply, DMM, and active loads put the coordination, wiring, and control burden 100% on the user, whereas the SMU significantly simplifies setup and operation. Because of its built-in sourcing capabilities, an SMU can minimize overall measurement uncertainty in many applications. The first diagram shows the basic voltmeter configuration for an SMU. Here, the built-in current source can be used to offset or suppress any system-level leakage currents, such as cable noise, that could cause unwanted errors in voltage measurement applications. For current measurements, the SMU's built-in source and feedback ammeter design work together to keep voltage burden low and enable low current measurement to sub-picoamp levels. DMMs do not have the built-in source and typically have shunt ammeter designs that limit low current capabilities to nanoamp levels. Finally, for resistance measurements, the SMU architecture offers full flexibility over the amount of current or voltage being sourced into the device under test. DMMs have fixed current source values that are dependent on the range being used to measure resistance. So you might be asking yourself right now, why should I use the SMU instrument? What makes the SMU so different than the bench power supply and DMM? Let me answer these questions. One key difference between the SMU and the DMM is how it can measure resistance. SMUs offer fully programmable source values for measuring resistance. One of the advantages of the SMU over the DMM is that user can choose whether they want to source voltage or source current to make the resistance measurement. This can be valuable for protecting sensitive devices under test, or for measuring extra high or extra low resistances. The DMMs only use fixed current sources that are dependent on the range being used to measure resistance, which puts a limit on the overall range of resistance that can be measured. When using the SMU to measure high resistance, the source voltage method is preferred, and for low resistance measurements, the source current method is the best. Here is a quick description of how an SMU instrument is different from a typical power supply. The SMU is optimized for both speed and precision. Therefore, the rise times are much faster than the power supply. And the measurement uncertainty of the SMU is much lower. In addition, SMUs provide superior dynamic range for both sourcing and measuring, which ensures best possible accuracies regardless of device impedance and signal levels, compared to the best programmable power supplies. Capturing your true device leakage current levels down to femtoamp levels will not be possible otherwise. This enables you to use SMUs in many more types of applications. A typical power supply only sources voltage and/or current. We refer to this as two-quadrant or source-only operation. An SMU sources and sinks, therefore has full four-quadrant operation, acting as both power supply and an electronic load. This can be especially valuable when characterizing power management components. During source or sink operation, the SMU can simultaneously measure voltage, current, and resistance. Another key feature of an SMU instrument is its sweeping capability. This enables custom programming of the source, delay, and measure characteristics of your test and really boosts productivity. Pulse sweeps greatly reduce the power dissipation within the device, so the effect of temperature are virtually eliminated. Regardless of whether you are new to instrumentation or an experienced engineer who has been making measurements for many years, there is no denying that all of us are being influenced by consumer electronics like smartphones, tablet computers, and digital cameras, which are fundamentally changing the way we interact with electronics. Modern SMUs with touchscreen graphical user interfaces can make you more productive, improve the component selection process, and shorten the design cycle time. The see it, touch it, do it aspect of touchscreens not only makes consumer electronics more fun to use, but can enhance the user experience with bench instruments in much the same way. Because so many of us are already familiar with touchscreens on the handheld products we interact with every day, we will find the transition to instruments that use touchscreens a second nature, not only for configuring measurements, but for displaying results either numerically or graphically. Rather than struggling to configure measurement functions using cumbersome multi-layer menu structure and confusing multifunction buttons, smart technology users are more likely to prefer the flatter menu structures with which they are already familiar, like the array of app icons displayed on a tablet or a smartphone. What's more, graphical touchscreen instruments can provide real-time graphing right on the screen to increase the speed to answer and enable you to make smarter design decisions. Let's take a look at how Keithley's new SMU instruments are changing the way we interact with instruments. SMUs like Keithley Model 2450, 2460, and 2461 source meter instruments feature Keithley's new Touch Test Event user interface, making IVy characterization as simple as possible. Setting up a sweep on these instruments is a breeze. To perform a sweep on a model 2450, 2460, and 2461, go to the main menu, then tap the sweep icon under Source to bring up the sweep settings screen. All of the settings required to configure a sweep can be found on a single page that can be scrolled through with a swipe of a finger, eliminating the hunting through menus associated with traditional SMU instruments. Once you have configured the settings to your liking, press the Generate button at the top of the screen to configure the instrument for sweep operation using your settings. The sweep is now ready to be run, and you can view the test results such as the MOSFET family of curves right on the front panel. The touch test event interface of Keithley's Model 2450, 2460, and 2461 source meter instruments allow for immediate visualization of collected data. To view the data on a graph, go to the main menu, then tap the graph or histogram icon under Views. The graph appears on screen with the voltage on the x-axis and the current on the y-axis to properly display the characteristic IV curve of the device. Depending on the test you're running, the histogram view provides statistical data of the measurements as well. The data is plotted on the graph in real time, allowing you to visualize the IV curve of the device as it is gathered, thus providing you immediate insight on the behavior of your device. This live plotting is also useful for seeing device failure as it occurs for monitoring the progress of very long sweeps that may contain hundreds or even thousands of data points. Thanks to the touchscreen interface, pinch and zoom gestures can be used to zoom in and around the graph and view your data up close. In addition, you can use the built-in scope-like cursors to gain deeper insight into your measurements. These graphing capabilities simplify the selection and characterization of 2- and 3-terminal devices. After collecting the data, you'll most likely want to save it for further analysis and reporting. Saving the IV sweep data on the Model 2450, 2460, and 2461 is just as easy as setting up the sweep. Go to the main menu and select Data Buffers under Measure. Tap the buffer where the data was collected to bring up the settings for that buffer. Tap the Save to USB button to save the data on a file on a USB thumb drive that is plugged into the front panel. Use the on-screen keyboard to name the file and then tap OK to save it. The data is saved to the USB drive in a comma-separated values or CSV format for further analysis in spreadsheet programs like Excel. Earlier, I discussed making measurements on power management devices. Source measure units simplify power measurements by combining the capabilities of a high-resolution power supply with those of a precision digital multimeter. SMUs can source a voltage to power a device, then measure its current draw, allowing you to measure the device's power consumption using only a single instrument. In addition to sourcing power, SMUs have the ability to sync power, enabling them to act as an electronic load. This means with a single instrument, you have the ability to measure device power output as well. These instruments will even do the power calculation for you and display the power measurement in watts right on the front panel. Configuring SMUs like the Keithley models 2450, 2460, and 2461 source meter instruments to measure device power consumption is incredibly easy. Start by pressing the function button, then tap the source voltage and measure power button. Next, tap the source voltage level button to set the voltage source to the proper level for your device. Tap the limit current level button to set the current limit. This should be set to the maximum level allowed by your device before it could be damaged. Finally, turn the output on and watch as the power consumption measurements appear on the screen. As I said earlier, in addition to being able to source power, SMUs can sync power as well, making them great for measuring power output of a device. Like measuring device power consumption, measuring device power output using the Keithley models 2450, 2460, and 2461 source measure instruments is also incredibly easy. First, press the function button on the front panel, then tap the source current and measure power button. Using a current source, you can set exactly how much current you want to draw from the device under test. Next, tap the Source Current Level button and enter the current level to draw from the device. Note that you need to set the current level to a negative value so the current will flow out of the device and into the SMU rather than the other way around. Next, tap the Limit Voltage Level button and set the voltage limit of the SMU. This should be set to a value larger than the output of your device so that the SMU can output voltage large enough to not short the device. Finally, press the Output button to turn the output on and start taking measurements. Keithley source meter instruments with a touch test and vent interface can greatly simplify the process of measuring power efficiency through the use of Keithley's test script processor, or TSP, and a virtual backplane interface known as TSP-Link. TSP is a technology that allows you to load and run simple scripts right from the front panel of the instrument to perform more specialized measurements like power management, power efficiency measurements. TSP-Link is a technology that allows for the communication of instrument commands, data, and triggers between instruments that include TSP. Using TSP and TSP-Link, power efficiency measurements, which require two instruments to make, can be performed from the front panel of a single instrument and the power efficiency calculated and displayed automatically. Let me show you how. To perform power efficiency measurements using TSP and TSP-Link, you can create a test script that controls two SMUs and calculate the efficiency. This script can be saved to a USB flash drive that can be plugged into the front panel to run. From the instrument's home screen, tap the word No Script at the top of the screen to display a list of available scripts to run. Tap the item USB1/powerefficiency.tsp from the list to load and run the power efficiency script from the USB drive. This simple script handles most of the setup work for making the measurement and only asks for two pieces of information from the user. Enter the input voltage to source into the device, then enter the output current to draw from the device. The script configures the instrument, makes the measurement, then calculates the efficiency and prints the results to the front panel. With TSP and TSP-Link, power efficiency measurements are now incredibly easy. I have shown you how easy it is to use a modern SMU instrument that can be used for 2- and 3-terminal device characterization along with power management device testing. But there is much more to the touch, test, and vent experience to set up tests quickly and getting your results faster, such as bringing the same capabilities to a mobile smart device platform. Tektronix has made great strides to simplify the task of 3-terminal device testing by harnessing the power of mobile electronics. With the new IVy mobile app, Tektronix has brought to the world of test and measurement the power of simplicity that mobile apps have given to consumers and allows you to perform complex measurement tasks incredibly easy. The Keithley IVy app allows you to interactively test 3-terminal devices with minimal setup required using Keithley's Model 2600B series of single and dual-channel SMUs. To test a 3-terminal device with IVy, start by choosing the voltages to be applied to the control terminal of the device. These are the levels at which the other 2 terminals will be characterized, and a separate IVy characterization curve will be drawn for each control level. For a MOSFET device, these levels will be the gate terminal voltage at which the drain to source IVy relationship will be tested. Next, set the current limit to protect the device from an overcurrent condition. Finally, tap the output on-off switch to turn on the SMU outputs and begin testing. Dragging the slider at the bottom of the screen sweeps the voltage across the device terminal. As the slider is moved, an IVy curve is drawn on the screen for each control voltage, creating the characteristic IVy curves for the device. Saving this data is easy too. Simply tap the Share button in the upper right of the screen, then select where to send the data. Using the built-in sharing services of your tablet, You can easily send the data via email, save it to the cloud, or use any other sharing services available on your device. With the new IVy app for Keithley Series 2600B SMUs, 3-terminal device characterization is incredibly easy on any Android or iOS device in the palm of your hand. In just 3 simple steps, you can now do what used to take hours of instrument programming. IVy enables the engineer to visualize instant responses through immediate interaction. If you think you saw something on the curve that caught your attention and you want to see it, if it is repeatable, all it takes is a simple swipe to change the source value and instantly see the response. If you want to share these results with another engineer to review what you saw on the curve, IVy allows you to share screenshots and the data, all of which can be emailed if your handheld device is connected to a network. IVy truly can reduce test time and improve productivity. Tektronix offers a complete set of solutions for component DC characterization and selection. Our Keithley source measure instruments cover the broadest dynamic range available, from nanovolts to kilovolts, and from femtoamps to 100 amps. And we have a variety of software tools to help improve your productivity and enable you to learn faster, work smarter, and invent easier. But the instrumentation is only part of the answer. As part of a completely engineered solution, also needed are text fixtures, probe station interfaces, high-performance cables, and control software with complete test libraries. Tektronix offers a variety of completely engineered solutions for nearly any component test need. The purpose of this web seminar was to provide you with a good overview of what it takes to characterize devices that you may have to select to use in your design process. Source measure units are well suited for these tests. They provide the utility of multiple integrated instruments without the hassle of integrating separate instruments together and the need to worry about triggering, timing, and synchronization. They even can be space savers on your engineering bench or workstation by eliminating the need for power supply and DMM. Finally, modern graphical user interface enabled by touchscreen technology makes it easy for the first-time instrument user, the experienced user, or even a user not familiar with making electrical measurements to get their work done quickly.
Find out more at Vicom's website.